Okay, so this tutorial, this is the one we've been looking at. And I'm actually not so sure how much to cover up this first part, just doing the basic mole balances. But anyway, let's just talk through it, and you can tell me whether you'd like me to speed up or slow down or whatever it is. So in this first one, this is the reaction. So 2 of A and 1 of B gives us 1 of C and 2 of D. We are given the kinetic rate constant. We aren't told anything else. We aren't given flow rates and concentrations or anything like that. We are told derive the design equations for each of these, which I'm not actually going to do right now because we've done all of that in detail in the last one. But maybe let's just start with this part. It asks us just for the relationships among the rates of formation of each of the species and with component A in particular. And, what's the relationship among, well, what is the relationship between the current number of moles or concentration and the conversion? So I'm just going to start with a new document here. So let's just repeat the reaction. Okay, and then we want to know how do each of those rates of formation look? And there is a general formula, and that's shown in the notes and all of that, but let's just try thinking our way through it first of all. So there's a certain rate of formation of A, so let's just think of that as the basis rate. And then let's think about component B. And if you look at this, it takes 2 of A to react with 1 of B. And what that tells us is that B will disappear half as fast as A will disappear. And of course, then if we are talking about rates of disappearance, we should say minus RA. And then for B, so we said B is going to disappear half as fast as A. So we can say B is disappearing, and it's going to be half as fast as A is disappearing. So it's going to be divided by 2 over here. And by the way, this is a common kind of error that we see, that there's a tendency to say, okay, it's 2A plus B, so I need to say 2RA equals B. Just think carefully through it. When we say we've got twice as much of A as B is being consumed. So that's in terms of amount being converted. In terms of the rate at which B is consumed, you can see here, for every 1 of B, 2 of A are consumed. So that's why RB minus RB is minus RA over 2. And then for C, we can see for every 2 of A, 1 of C forms. So we can say also RC. So C is formed, so that's a rate of formation, and that's equal to, and A is a consumption, so R sub A. So that's RA there. And then you have to be careful with your signs and things, right? So the stoichiometric coefficients here are signed, right? So this is a -2. This is a -1 hidden here next to the B. This is a +1 and a +2. And then if we think about the example, if we think about the numbers here, if we say, let's take a basis of 100 moles per second of A being consumed, then we can say that for every 100 moles per second of A being consumed, let's talk about D now. We can say 200. No, not 200. Let's work with C, right? Not A. I want a pair with the different stoichiometric coefficients. So for every 100 moles per second of A being consumed, 50 moles per second of C is formed. Right, so when we write it in the text form like that, that makes perfect sense to us. But of course, we also have to be able to write it in a nice equation form in terms of R and our stoichiometric coefficients. So, so R is strictly the rate of formation of component I. So when we write minus RA over 2, what we actually mean is the rate of formation of A, that has a certain value behind it. So if we have here 100 moles of second, 100 moles per second of A being consumed, then it means our rate of formation is minus 100 moles per second, right? So just be careful with that. When we say being consumed, we understand that to be minus a negative number. So this is a negative number in terms of rates of formation. So RA itself is minus 100 moles per second. So then minus times a minus, that is our 100 moles per second divided by 2. So that's overall plus 50 moles per second. And so when we write it here, 50 moles per second, then we get correctly 50 moles per second of C is formed. Right, so that's the way to look at it. You may have negatives in your formulation, but in terms of your symbols, the numbers behind these rates may also have signs. And then you have to be careful to multiply them correctly when you use this equation. Okay, so Andile says, can you make an example if A was the one disappearing as half of B? So that's effectively what I tried to do over here. So let's see if the reaction was, okay, so you wanted the other way around. So let's say if we have something like this. So let's look at an example like this. So now again, let's stick with a basis of 100 moles per second of A being consumed, but now we are producing twice as much B. So we can say on a basis, right? So without using any kind of formula, just looking at this expression, we can say on a basis of 100 moles per second of A being consumed, then 200 moles per second of, of B will also be consumed, right? And then in this case, you'll say your rate of consumption of A, so minus RA, and then we want to write something times RB. So first off, we know B will be consumed as well, so that's a minus. And then if we look at this, we can see B is consumed twice as fast as A. So in this case, we will say 2 times RA. Does that cover it, Andile? Okay, thank you. So so that's and just to avoid confusion, so that's a different stoichiometry. I'm putting that on the next page. So here, so we've got 100 moles per second, and so those are the relationships. So once more, in your formulation, in your general equation, you may have signs, right? Minus a minus sign, for example, there, and that doesn't change the fact that behind the symbol, you may have a negative number as well. So in this example, this was minus 100. So you preserve that minus sign, you correctly use that minus sign because that is by default a rate of formation, and you have to multiply them to get the right numbers. Okay, so that's what we can say, and just to complete it, we can say RD equals, and you can see the same amount of D and A, the amount of D formed is the same amount as A consumed. So the way to write that in symbols is RD equals minus RA. So that completes that. And then we can write a general form. We can identify a general way of looking at this. If we say Ri over nu I equals Rj over nu j, like that. Okay, and if you look at what we have over here, so if we just use the formula for A and B, we would write here Ra, and then the stoichiometric coefficient for A here, it's a reactant, so that's a -2. And then for B, we can say here, the stoichiometric coefficient for B, that's also a reactant, so that's a -1. So that looks like that. And then if you look up here, it's the same equation that we have, right? So that agrees. So this formula fits for A and B at least. Then let's try for C and D as well. So again, we are going to have Ra, and we'll have a -2 down here. And then for C, the stoichiometric coefficient here is a +1, so that's just a 1 there. And then if we look at what we wrote for RC, you can see RC is -RA over 2, so it's the same as this equation. And then again, for completeness, we can do RD as well. So for RD, I'm just going to say here, it's D divided by its stoichiometric coefficient, which is a +2. And then if you look at what we wrote here, -RA equals RD, which is the same as this. So you see, it all agrees. This general formulation does apply if you use the correct signs for nu, right? So even though when we write the reaction equation in its standard form, we don't normally think of the stoichiometric coefficients as having signs, but they definitely have signs, especially when you want to use this expression. So you have to use the correct signs here, and you have to respect that this R is it's strictly a rate of formation. Okay. So that's the first thing we need to think about when trying to do our when developing our expressions. So in going back to the tutorial problem, so that's how we can write the relationships among the rates of formation. Okay, and the general relationship between any two components, we can write like that. This is quite easy if we have a single reaction. Of course, if you have multiple reactions, you can no longer use something as simple as this. Then we have to think about adding in the contributions from the different reactions. But we'll get to that later when we have multiple reactions. We'll stick with the single reaction for a fairly good space of time. All right. Now in part B, we want to write down the number of moles of each component in terms of conversion of component A. And this is something you'll see again and again in reaction engineering. Quite often, we don't want to write our expressions for every single component. We'd rather pick one basis component, and usually that's component A. So we usually pick some basis component and we work everything out with respect to that component. And that helps us with reducing the number of variables. Obviously, in doing our calculations, we don't want hundreds of variables floating all over the place. So for example, conversion, we'd like to get away with just one definition for conversion. So we'd rather pick one component and define the conversion based on that one component. And it's quite important to keep in mind that you always have to reference that component correctly, because you can see that the different species react to or they are converted by different amounts in terms of their absolute number of moles, right? So B, for example, consumed half as fast as A. So the conversion of B will have a different, the actual value of the conversion will not be the same. And be careful when you think about conversion. Even though conversion is a nice dimensionless number, it's not the same for all species. If the same thing happens, right? Let's just make a quick sketch here. So if you have your batch reactor sitting here and your species react for a certain period of time, and so it's the same reaction that's happened here. All the species are reacting and forming in the same event, right? So even in the same event, you can define different conversions for each component. So XA is generally different to XB and to XC and so on. So we don't like to work with so many. We don't want to have to define a conversion for every single component like that. So instead, we'll pick one out of our components, and we'll reference all the other changes with respect to that. So in the case of this example, let's again take 100 moles per second of A being consumed. Let's also specify that of 100 moles per second of A being fed. Let's just say that's the feed rate. It's not the consumption rate. And also let's say 100 moles per second of B being fed. And you would automatically want to tell me, well, don't feed 100 moles per second because B is consumed half as fast, so you only need half as much. So I'm deliberately not wanting stoichiometric amounts here, right? So let's see what we get. So let's say conversion of A is XA equals, let's just say 0.7. I don't know if we'll actually use this number, but let's go with that. So then we can say moles of A after that conversion, moles of A is equal to moles of A initially, and then of course times 1 minus XA. So the moles of A left over will be 30 moles per second. And clearly, then to work out the moles of B, we know that twice as much twice as much is converted in A. So half as much of B is converted. So 70 moles per second have been converted of A. So 35 moles per second of B have been converted. So we can say NB is equal to NB naught minus, and it's going to be half the amount of A that has been converted. So the amount of A that's been converted is, of course, NA naught times XA, and we want half that amount, so divide by 2. So NB naught, that's 100. NA naught times XA, we said was 70, divided by 2 is 35. So what's left over is 65 moles per second. So that's NB. And then for component C, well, we know that, let's assume that we are not feeding components C and D into the reactor. And we don't expect that we would need to, because these are products. We are trying to form them. We don't expect we would feed product in, but you can easily imagine a case where a reactor has a recycle or something like that. So that's why it's not trivial to say that there's none of them. But anyway, we will assume we are not feeding C and D. So we don't have to worry about an inlet flow or anything like that. But C is formed half as fast as A is consumed. So we can say NC equals NA naught times XA. So that's the amount of A that is consumed. And then we want to divide by 2 to preserve the stoichiometry. So we get 35 moles per second of C, okay? And then ND, so the moles of D that form is equal to the moles of A that's consumed. So we get the same amount of D formed as A is consumed. So NA naught times XA, that's going to be the amount of D, and that's equal to 70 moles per second. Okay, so that's how you can do that if you kind of use your brain and work out each one. But if you don't want to use your brain, then you can use the formula. And there's a nice easy formula, which we can write as Ni, the number of moles left over of component I, that's equal to Na naught. And we have here a capital beta sub I minus mu sub I over mu sub A times XA. So let's see if this has worked out. And let's start with component A itself. Noting here that beta I equals, and this is beta A. So it's a vector of each of our species. So each of these betas are nothing but inlet flow ratios. So these are Fi0 or Fa0 divided by the reference component. So the reference component is Fa0. So that's component A, component B, component C, component D. So we'll write these. So those are how we define betas, right? And we can see here Fa0 over Fa0, that's equal to 1. And then Fb0 over Fa0, we did choose 80 moles per second here. So, 100 moles per second of B. So that's also a 1. And then we said there's none of C coming in. So that's 0 over 100. So that's a 0, and that's also a 0. There's none of D coming in as well. So theta A, B, C, D, 1, 1, 0, 0. Okay. So we can work this out we can use the general formula and say NA and then Na0. So theta A is a 1. And then you've got nu A over nu A, which is also a 1. And you've got XA. So there we do get the expression that we expect for Na. And then for NB, let's use the formula again. For NB, we've got NB equals Na0. Theta B, we've just said is a 1. And then you've got nu B over nu A. So nu B over nu A is going to be -1 over -2. So it's a half. So this is XA over 2. And if we look here, you've got your minus Na0 XA over 2. Right, so this part is correct as well. And then for NC, that NC equals, and our theta in this case is a 0. And here we've got C is +1 divided by a -2. So this is overall minus plus 1 over, sorry, I should have done it from here. So let's just copy it like that. So this is NC. This is a 0. And we've got a plus 1 over a minus 2. So that's minus a half. And then times a minus here, that's going to give us plus 1/2. So this is plus XA over 2. And if you look here, that's what we said earlier, right? So that's NC. And then for D, ND is, and the theta here is a 0. And the nu is I think that's a plus 2, and this is a minus 2. So overall, this is going to be a plus 1. So it's plus XA. And that's what we had over here. Okay. Okay, so this general formula works no matter what stoichiometry you have and no matter what your inlet amount is. So let's say we did have recycle and we were feeding some of C and D in, then we would just use those quantities here for our theta as well. Okay, any questions or comments on that? So that's how we can get our molar amounts. Now what we want is a relationship between the number of moles. Well, that's what we just did, right? So we did part B where we worked it out for each component. Then we used the general relationship, and now it's asking us about molar masses. It's saying here B, C, and D. We have these molar masses. So what's the molar mass of component A? So how would we start working this out? So I don't want to keep droning through the session. So please, maybe can someone give us an idea? How would we start working out this molar mass? What's the main principle to work out molar mass here?
We can use the conservation of mass.
Yes. So that's perfect. That's exactly right. So we know that the number of moles may be changing. Well, in this case, the total number of moles is not changing, but still you could have a reaction where the number of moles overall is increasing or decreasing. But be that as it may, the mass will still be preserved. So as you say, we can use the principle of conservation of mass. So the mass before the reaction and the mass after the reaction is the same. And we can always estimate the mass of our mixture if we take, maybe we can write something general here. So if we know the number of moles, then we just have to multiply by the molar mass. So we can say the sum over all our species I, if we take the number of moles of our component and multiply by the molar mass, then that will equal, so let's say it's changing with time. So the mass of our species, how can I say this? Maybe before and after reaction, right? I don't want to say the mass can't change with time. The mass can change with time, but the point here is not due to reaction. So let's say before reaction and after reaction. So the mass before reaction and after reaction is going to be the same. And so if we think about this reaction, let's just copy it down here. So if we think about before reaction, let's do it on a basis of, again, 100 moles per second of A reacting, or let's say 1 mole. Let's say 1 mole of A reacts, 1 mole A reacts, okay? Then the number of moles used in the reaction, the number of moles consumed, or the mass consumed, and we'll say consumed like this because we don't consume mass. So the mass that disappears on the left-hand side, that's going to be molar mass of A, and that's times 1 mole plus, and then the molar mass of B, and that's a half a mole has reacted there. So times 1/2 equals, and so the mass consumed equals mass produced. So we can say molar mass of C, molar mass of C times, and we can see for every 2 moles of A, there's 1 mole of C. So this is times 1/2 plus molar mass of D, and this is in the same amount. So what we want here is molar mass of A. So we can just solve this for A, right? So that amount minus molar mass of B over 2, that's going to be our molar mass of A. Okay. Now we are told that we are feeding to a CSTR in these amounts, right? 30 moles per cubic meter for each one. So in terms of concentration, we can see also it's not in stoichiometric ratio, but that's fine. That is what we were given. So we have to work with that. And then we are given the volumetric flow rate. We are given the volume of the reactor. And we want to know what are the production rates. So whenever we see something like this, the first thing we like to do is work out the space-time and just kind of sit back and think, how long does it take to move through this reactor? So we've got, so we can say our space-time tau equals V over Q. So remember what we said, we can think of T as the, or tau as the time taken for that volume to pass through in that flow rate. So in this case, we have 50 moles per cubic meter, 50 cubic meters for the volume. And we have 0.0417 moles per second, 0.0417 cubic meters per second. Cubic meters. Cubic meters. So if we work this out, we stick the numbers in. So I'll just keep Excel open here. So 50, 0.0417 equals that divided by that. So I'm just going to call that 1,200. So 1,200 seconds. Okay. So that tells us we have 20 minutes. So we have 20 minutes as the average time that our fluid is spending in that reactor. So it's always useful to think about, do these numbers make sense? How realistic is this process? So 50 cubic meters, by the way, it's a fairly standard size reactor. And 20 minutes, that's not, it's a little bit fast, but not unthinkable. So this seems okay. And this is happening in a CSTR. And we don't know anything about the reaction. We're going to have to assume this is an elementary reaction. So let's just say here, minus RA, rate of consumption of A, is equal to A times CA. What was this? 2CA. Yeah. So it's CA squared times CB. So that's our rate expression. And we have the kinetic rate constant, and we need CA and CB. Now we have expressions for the numbers of moles. And maybe we can just copy this. And I'm just checking off these numbers because clearly we are not following these numbers anymore. Right, so these as general expressions work fine for us. We can improve this. We can write this in terms of our thetas instead. So we could write here CA naught, and it's theta B, and then we're just going to use brackets here. Okay, so we have this from earlier. And if we assume, let's say this is a liquid phase reaction. Does it say? So it doesn't say what phase this is. So I'm just going to assume it's a liquid phase reaction. Maybe we'll do it again for gas phase. But if it's a liquid phase reaction, and if we assume the volume doesn't change, so if volume same before and after, then we can divide both sides by the volume, and we'll get CA and CB. And so dividing by the volume, this is CA naught. Now for our problem, we are given that it's 30 moles per cubic meter. 30 moles per cubic meter for A and for B. So theta B, so it's 30 divided by 30, so that's a 1. So we can replace this by a 1 here, right? And so our expression, our kinetic rate expression looks like this. So we can replace all this by this. So we need to say this one squared. So we can say here CA naught squared, and then we also have to square this part, right? So that's CA squared, and then we have to multiply by CB. So CB has a CA naught over here, so we need to square this, cube this, and then we have this part, and this is not the same as this form, so we'll need to write this like that, without the CA naught, with cube CA naught. So this is our kinetic rate expression. And you see it's nice and compact. It's all written in terms of component A. It has only the variable XA in it. Okay, so that's our rate expression. But we want this for a CSTR at steady state. We did see last time for steady state CSTR, FA naught X equals RAV, like that. And if we divide both sides by Q, so let's say here, divide by flow rate Q, then we get, so FA naught divided by Q, so it's the molar flow rate divided by the volumetric flow rate. This is going to give us the concentration CA naught. And then here we are also dividing by Q. So volume divided by volumetric flow rate, like we said earlier, that's nothing but the space-time. So we can rewrite this as CA naught times X and on this side we've got tau, which is a number we've already worked out. This RA, we have an expression for here. And we can get rid of a CA naught. We can divide by this CA naught. So this gives us CA naught squared here. And that's basically it. That's our equation. So what we can do with this now is understand what the remaining variable is. So we've already been given the volume and the flow rate. So tau is fixed. We have worked out tau is 20 minutes. CA naught is simply given to us as 30 moles per cubic meter. And the kinetic rate constant is also given. So if we look here, the kinetic rate constant K is defined as 2 times 10 to the minus 4 here. So you see then that the only unknown left in this equation is XA. I should have said here, XA. Right, so we can solve this equation for XA. So number one, you'll want to multiply this out and solve it. And that will tell you what conversion we are getting in this reactor. And one of the things we should do is take a step back and think about, is it true that we should be able to work out the conversion for this CSTR? So here's our CSTR. We are fully specified in terms of the reaction rates. So our reaction rate, the expression at least, is given. We do know the concentrations coming in here, CA naught and CB naught. So we know the concentrations coming in, we know it's perfectly mixed, we know there's an exit flow rate. So this, in a way, constrains us to a given conversion. There is a certain conversion here that is going to be achieved. I don't know whether you find it weird I'm saying this, like I'm just stating everything again, but to me, when you look at a picture like this, you try and imagine how much free play is left over here. So for example, if we hadn't specified any of these, then you can almost immediately feel, hey, there's still something floating. I won't be able to work this out because I don't know what's coming in here. But if you look at what we are given everything at the inlet, and we are given what nature does, right? When we are given a kinetic rate expression, that means nature has told us everything there is to know about this reaction. So given that I also know the volume and the flow rate here, so I know exactly how much time it's spending here, and I know how much is coming in, then that will constrain me to a certain conversion. Or you can just look at it in the equation. So if you look at the equation, you can see everything is specified except XA. So we have enough information to solve for the conversion here. Okay, any questions or comments on that? So that's what we have in a CSTR. We are also asked, what's the steady state production rate of C and D? Well, the first thing we have to do, we can see, is solve for the conversion. If you do have the conversion, then you can see you can work out the rate at which A is being consumed. So if you've solved for conversion, then you can just stick it in here. We've got CA naught, we've got K, so we can solve for RA. And then you can just use the relationships between RA and C and D over here to calculate those rates as well. Okay. And here's another slightly more interesting one. So what should the volume be if we want to achieve this conversion for A? Right, so that's slightly different now. Here's our expression. So this is still true, but we should rewrite this tau as a V over Q, V over Q. Right, so we assume that we are not changing the flow rate. So assuming the flow rate is the same, now we are simply given X. So we are given 70%. So we substitute 70% for all these XAs here. K is still the same. That's nature. That's the kinetic rate constant. You can't change that. We assume that we are still feeding at 30 moles per cubic meter. So everything is now defined except for this V. So we can solve for the volume here. So yeah, I don't actually have the numbers on me, but yeah, you can look at XA and see whether the volume, right? If XA is lower in the first case, so let's say we had 0.5 in the first case, and then if you had 0.7 in the second case, then your volume that should be higher. You should need a bigger volume to reach 0.7. Another way to think of it is you need to achieve a greater conversion, you need to spend more time in the reactor. So the bigger the volume of the reactor, the more time you are going to spend there, right? If you're feeding at the same flow rate, if your reactor gets bigger, your fluid is going to spend more time in that reactor. Okay, any questions or comments there? Okay, so that's the first one. Now this is another perfectly mixed reactor. I don't think this is too similar to the other one for us to repeat. Yep. Does anyone have any questions about this one? Okay, so you can do this one as well, and then here. So now we have a PFR. So A and B are fed to a PFR. You can see the same inlet concentrations. We have the same volumetric flow rates, the same volume of reactor. So it's actually the same system. We assume that the constant and the reaction are the same as well. And so this question is simply, if we use a CSTR, a PFR instead of a CSTR, then what's the conversion of component A? Yeah, so maybe let's just derive the expression for that. So for a PFR, I'm just thinking, should we derive the whole thing? Well, we can say that for a PFR, the expression that we have is minus F A naught. And then you've got, let's see, the way we did it last time was as a, you can write it as dCA d tau equals RA. So if you look at what we did last time, we derived the expression for the PFR in this way. And you could expand this out as, so your tau here, of course, is V over Q. And V we could rewrite as A times Z, right? And Q you could rewrite as A times U. Oops. As A times U. So volumetric flow rate is cross-sectional area times velocity. So the areas can cancel. So this expression is U times dC dZ equals RA. And you may want to check the units quickly. So CA, it's moles per cubic meter up here. And then you've got meters per second for velocity, and you've got meters here. So U over dZ is 1 over time. And so you've got moles per cubic meter per time. And we know that reaction rate is moles per cubic meter per time as well. So the units are right here. So that's our equation for the for the CSTR. Let's see. Well, we are, yeah, in fact, there was no real point to going and changing the variables because we are given volumes and flow rates. So we may as well stick with this. Okay, so this equation, we just need to substitute for our rate expression here. And the CA can be written in terms of our initial amount. So we're going to write here minus CA naught and XA. And by the way, the minus sign has crept in because, of course, CA equals CA naught 1 minus XA. So when we differentiate, this is minus dxa dt, right? So that's there. So all we need to do is integrate this equation with respect to tau. So we integrate from 0 to this tau value, 20 minutes, right? 1,200 seconds. And then we can compare. So I don't have the numbers on me, but which one do you expect to be higher? So show me that I'm not droning to myself here. Which is higher? So we'll get a certain X here. So for the for the PFR, that's what we have. So we'll get a certain conversion here. Will that be higher or lower than the CSTR case?
So I think it will be higher than the CSTR for the same volume.
Thanks. So why do you say that?
I think it's because of the, I'm looking at the performance equations. The CSTR can perform low conversion compared to the PFR for the same, for the CSTR will require a huge volume compared to the PFR.
Thanks for that. So that's exactly right. So remember we said last time that the CSTR is stuck to the same low conversion everywhere. So because it's perfectly mixed, and that seems like a perfectly normal engineering thing to do. We'll say, yeah, stick a nice stirrer in, mix everything up, let it react. Seems obvious, right? But what happens then, what that means then, is that you've got the same conversion everywhere inside the CSTR. So you've got the same conversion, that you've got the same concentration everywhere. And that means if you have a high conversion, conversion is the variable here, but in the same volume, so you've got the same 50 cubic meters in both cases, but in the case of the CSTR, you are stuck to the exit conversion. So we know the exit conversion here is some value X, and we know that the concentration depends on the conversion. So the concentration equals the inlet amount, CA naught 1 minus X. So when X is large, CA is small. And in fact, if you just look at the equation, when X is large, when it's closer and closer to 1, this number is going to become closer to 0. So our net rate of production, that I should be pointing here, our net rate of production will be quite low here, right? So our net rate of production is quite low if XA is large. On the other hand, for the PFR, when you have a high conversion, you won't see that conversion until right at the exit, right? The conversion, the observable conversion in the case of the PFR is out here. So you've got that high conversion here, but over here, you've got a conversion of 0. So you start out with 0 here, which means you have a high concentration initially, and then the concentration drops like that. So you have regions where the rate is high. So you will accomplish the same conversion in a much smaller volume, in this case, compared with the CSTR case. So that's right. So the PFR, we expect to see a higher conversion. So please do work these out, right? Please do integrate this equation. You can just use some ODE integrator and do this, and you should see a much higher conversion. Okay, so that was question 3. Any questions or comments on question 3? Okay, then that's a good segue into question 4, which is using the so-called Levenspiel plot. And the Levenspiel plot actually helps us see quite clearly and obviously this difference among the 3 reactor types. So just to explain what the Levenspiel plot is, first we recall that we had established these as our design equations last time. So we had derived all these equations, and of course for the batch reactor, DDT of something. For the CSTR, we don't have any derivatives, it's just a straightforward algebra. And for the PFR, as we saw just now, it's a DD tau. So those are the 3 equations that we have. And when we look at this equation, we can see, well, we can't see it as yet. If we take these equations and then expand out for volume and flow rate and initial amount, right? So let's take the batch reactor. If we rewrite this in terms of your, let's see, what did we do here? FARI. So this initial concentration here, we can write that as the initial number of moles divided by the volume, right? So we can start with doing that. And then we can say, okay, for the batch reactor, what really matters to me is how long must I let this run for, right? So different things matter in the different reactors. So in the case of our CSTR, right? So let's say we have the same volume reactor. In the case of the CSTR, we might want to know how fast should I feed this reactor? So that could be a variable of interest there. In the case of the batch reactor instead, our question might be, how long should I let this react for? So what is my final time going to be? Because I can leave things here to react as long as I want. And we will get a higher conversion as time goes on. But I likely want to use this reactor over and over again, right? Overall, I want to think in terms of a year, how much product did I produce? So I'm not going to let this reactor just run on and, it's going to reach a saturation point. It's pointless letting it run so far. So I would rather stop somewhere. So what is this best time to run this reactor for? How long must this batch reactor run for? So that's something we can solve for. In the case of the PFR, this is also a flow reactor, so we might as well ask here also, given that it's the same volume, what is the flow rate that I want in this case? So these are some of the design type variables we want to start thinking about. So in our batch reactor, this is our design equation. And then if we look at this, what we could say is, well, if I integrate both sides with respect to time, then I'll get an expression like this. So I can work out how long to let my mixture react if I want a final conversion of XA. Or another way to look at this is to say, well, what if I have a fixed amount of time? let's say I want to cycle my reactor every 1 hour, then I can solve for the volume. Then that tells me how big my reactor must be for me to do that, for me to achieve that conversion X within time T. So that is the volume I need in the case of the batch reactor. Equivalently, we could say, well, what if I'm fixed in terms of my volumetric flow rate? So maybe my raw material is only available at a fixed Q. So what must my volume be in this PFR for me to achieve a certain X here? Or if it's a CSTR, same story. If that's my given flow rate, what must my volume be for me to achieve the conversion that I want? So in the case of the CSTR, of course, tau is like that. And we can convert our equation to this form. So we can rewrite it in terms of volume like this. So the volume that we need in the case of the CSTR is FAX over minus RA. And if you compare here, so you've got this X over RA, right? In the CSTR, it's a bit clearer. It's like X just divided by RA. Whereas in the batch reactor, it's the integral of 1 over R in X. So it's in the same positions, X over RA, but here it's the integral of RA with respect to X rather than a simple division. This is like your molar flow rate, right? Number of moles initially divided by the time. So that's kind of like an averaged molar flow rate, right? Na naught over T. It's quite similar to an FA in, if you think about it. So that's the CSTR. That's the volume that we need. In the PFR, we said that's our equation. And again, we can convert tau into V and Q. And so we can solve for V by integrating this equation. And again, you get this form. The integral of 1 over R in X, and then an FA in out here. So these are the three forms written in a more designed sense. So V, the volume of the reactor, how big must I make my reactor if I want conversion XA, right, XA in each case, given that I want to react at the rate of FA in or at the rate of a certain number of moles per second. So the three main reactor types, that's how I can get my volume. Now, the Levenspiel plot comes from looking at these equations and saying, we seem to have here a reaction rate and a conversion. And we know the reaction rates are functions of conversion themselves. So why don't we try plotting 1 over RA against XA, right? So once more, just looking at this, we seem to have generally a form that looks like this. We have that the volume that we want, so there's we want to calculate a volume, and it's proportional to something that looks like an X, something that looks like 1 over RA, the reaction rate. Oops. Put it like that. So the volume that we need is proportional to 1 over RA and something like an X. So we are seeing that it has a form that's like that. So in that case, then we'll say, and by the way, RA is a function of X as well. So it looks to us, let's try plotting 1 over RA of X versus XA. Right, so that's a Levenspiel plot. We simply take our reaction rate expression and plot it against XA. And it might seem strange why plot 1 over RA. And the simple motivation for that is it's just how RA seems to appear when we look at our design equations. It just turns out the reaction rate is inversely proportional to the volume in some sense, right? Because it's inversely integrated. Yeah. So that's what we do. Here's a Levenspiel plot, and this is a simple first order reaction. Let's see, there was something I wanted to say about that. Anyway, I've forgotten. So that's our Levenspiel plot. And this curve, this plot, is totally nature dependent, right? Nature determines this plot. So for a given reaction, there is a given rate expression. So whatever your reaction is, right? Like we started out with 2A plus B gives us, I don't know, 3C, whatever it is, right? So nature is reacting these species in this way, and there exists some rate expression which applies then. So that's some function in terms of the conversion, which we can express in terms of A. So nature has decided this. We can't really design this. That's something we'll see again and again in this course, right? We respect that nature has determined this relationship, that we have some species reacting. Again, we didn't choose all this. This is how it does react. And then it reacts because of the physical world we live in. It reacts in this way. So this is entirely out of our hands. And that's important to note, right? Because we like to know what can we fiddle around with as engineers, what is fixed, what are the things we can't do, what are the things we can do. So this curve, we can't do anything about this, right? We are told, so let's say the economics of the world has told us, you must produce component C if you want a profitable process. So, okay, so that's fine. Economics has told us that. But then when we go and look up, how do you get C? Oh, it forms in this reaction. Let's try and promote this reaction. Well, that reaction has this curve. So this is predetermined now. We can't do anything about this line. But what we can do is figure out how are we going to navigate our way around this? How are we going to design a reactor system given that this is the situation? And the first thing we could ask is, well, let's say I pick a conversion of 0.6. What reactor should I use? Should I use a CSTR, PFR? Well, what kind of reactor must I use here, given that this is my curve? So like our friend earlier said, use a PFR or a batch, don't use a CSTR. So does that show up in this design? How do we see that? Well, let's go back here. It's telling us that the volume, let's start with this one. It's telling us the volume that we get is the conversion over the reaction rates. And then another way to write this is to say, so we've got the volume. Let's make a semi-new space. So another way to say that is the volume that we need is, well, there's going to be an FA naught there. Can't do anything about that. And then we have an XA, and we have that over RA. So another way to write this, right, and you'll think I'm really being silly now, but another way to write this is just 1 over RA times XA. So 1 over RA times XA, right? So it's the same thing. I've just shifted the XA. And the reason I'm doing that is because now if you look at your Levenspiel plot, this is Y, right? Remember, on the Y-axis, we are plotting 1 over XA, and on the X-axis, we are plotting XA. So that's basically Y times X, right? If you look at your Levenspiel plot. let's just copy that so we can draw on it a little snip thing. All right. So let's just copy that on here. So we've got a y and an x. So let's pick a point. Let's say we want to achieve, okay, 0.7. So 0.7, we can read it up here. So that's my y value. And now so we want the reactor to have a conversion of 0.7, and we want to know what must my volume be then. Now let's look at what we wrote here. So we said the volume is, so we're going to assume this FA naught is fixed, right? So we're not going to worry about FA naught. But when we look here, it's y times x. Now we found a point. Here's the y value is here, and there's the x value. So the volume that we need for the CSTR looks like this, y times x. So we are going to need this volume, right? The area in this red box is proportional to the volume. Remember y. So your y value here. So that's my y value, and I'm multiplying it by my x value. So if I am multiplying y by x, that is basically the area of this box. Do you agree? Okay, so the volume that I need for my CSTR is proportional to the box, the area in this box here. On the other hand, if we look at the other equations, let's take the plug flow case. And I'm just going to snip it out. If we look at the plug flow case, that's a bit different. So in the plug flow case, we have this instead. And this one doesn't say multiply y by x. This one is saying integrate y with respect to x. Remember here, so y is 1 over RA, and we are integrating 1 over RA with respect to x. So geometrically, what's the integral of 1 over RA? So 1 over RA is y. So that's basically the area underneath the curve. So the volume required in the case of the PFR is the stuff down here in the blue shading. So you see your PFR needs less volume than the CSTR. The CSTR needs this additional volume here. Right? And so that's the first thing we notice. The other thing is in the batch reactor, we have the same situation. It's the integral of 1 over RA with respect to x. That's the same as the plug flow. Again, we have this kind of FA naught type of thing out here, but otherwise it's the same. So the batch reactor seems to have the same volume requirement as the plug flow reactor, and both of them have a smaller required volume than the CSTR. Does that, any questions or comments on that? Okay, so that's something we can observe, hopefully as interesting. And I guess everything we've said is what's here. So it's drawn a bit better here. So in the case of the CSTR, you need area 1 plus area 2, and your volume will be proportional to that. In the case of the PFR and batch reactor, it's only area 2. Your volume is only proportional to area 2. What are we doing here? So you are given this problem. Okay, this is a little bit of a different point. We'll come back to this. I want to keep going with this stuff. Okay, so So we can, so the nice thing about a Levenspiel plot is you can see in a quite geometric way how to do your design. It gives you a nice geometric interpretation for working out the volumes that you need to finalize your design. Now, let's look at some interesting case studies around this. So what if we have reaction inhibition? So let's see what that means first. So we've been talking about nice reaction rates, easy reaction rates like this one, rate expressions, I should say. So a rate expression like this, or, well, we even had that and times that and that, right? So that's all normal. Your reaction rate increases with your reactant concentrations. But there are certain reactions that have a kind of inverse relationship with their products, with their reactants even. So you can have a situation like this where your reactant actually poisons your system, or it might be that your reactant is interacting with your catalyst or something like that. But you do get cases, and sometimes both happen. So sometimes you get a case like this, that you normally, that most of the time your reaction is increasing with concentration, but when you hit certain values, then it actually starts to inhibit. So you might get reaction rate inhibition. So if your reactant is inhibiting the rate. So if you have a situation like that, then your Levenspiel plot may look different, right? So what if your Levenspiel plot, instead of looking like this, what if your Levenspiel plot looks like this, right? So 1/RA, and your conversion is here. So what if your rate actually increases with conversion, right? That's the way to say it's 1/RA. So your rate here is increasing with conversion. So in a case like this, which reactor is better? So any takers?
I think it's the CSTR.
That's good. So that's right. So the CSTR will actually be the better user of the volumes. So can you keep going with that? In terms of seeing it on the Levenspiel plot, can you walk me through how that would look, or what you would see on the Levenspiel plot to support that?
The taking a rectangular block from the Levenspiel plot, I can observe that the lower part has more volume or more area, I mean, than the upper part.
That's right. So the CSTR is going to be proportional to this block again, right? So as before, we picked a conversion to start with. So we picked XA over here, and then we read up a 1/RA, and we know that the volume of the CSTR is going to be Y times X, and that's there. On the other hand, the CSTR and the PFR, they are their volume is proportional to the area under the curve. So in their case, they will have an additional volume requirement, which is the part up here. So in the inhibition case, the high concentration causes your reaction rate to suffer, and you need more volume to achieve the same conversion, right? So there are these other cases. So nature can throw you this kind of curveball. Thanks. Right, so that's something that can happen. Now let's think about, what if both things happen? What if you get a normal increase of rate with conversion? Again, rate is 1/, so this is an increase of rate with X. And then past a certain point, you get a decrease. And again, this very much happens in real life, right? When you've converted past a certain point, you start to see inhibition influences. So could you suggest a way to, how would you choose, right? Let's flip it around now. How would you navigate this space? So as the UKZN graduate who's now available to solve a difficult reactor problem, how would you design a system or a process to minimize a reactor volume?
You can use more than one reactor.
Sure, and keep going. How would you, what reactors and where would you put them?
You can place them in series, one after the other,
Okay.
to use less volume while having more conversion.
Yeah. So if you look at this, you've got here, let's see, this is the part where you can see a block. So let's say we choose this as a kind of point where things are changing, right? You can see that the curve is inhibitory over here, and it's or rather, which way around should I say? It's inhibition over here. So we've got an inhibition influence up to this point, and then after that, it's a normal influence. So let's say we want to achieve a conversion over here. So that's what we finally want. So the volume, the smallest volume for us to use won't be to use a PFR first. If we use a PFR first, you can see we have to go full area under the curve. Whereas if we use a CSTR first, then that's we can get away with this small volume here. And then we don't want a CSTR here, right? So we want this final conversion, and there's the point on the curve, but we don't want this big block of volume for this CSTR. What we want instead is the integral area here. So this would be the optimal configuration for us. A CSTR that takes us up to this specific conversion. And then between these two conversions, we'll use a PFR or a batch reactor. Okay, so that's one of the things, right? Reactors in series. We can navigate this plane, we can navigate this curve in that way. That's what we said there. There is this useful number to bear in mind, the Damkohler number. So this number it's something like the extent of the reaction. So the Damkohler number, it's defined as your rate constant times your space time. In the case of the first order reaction, this number is dimensionless. So if you look at this, for first order, K is per second and T is seconds, so that's dimensionless. So that's the Damkohler number, and so you can rewrite your equilibrium amount in this way. I'm not sure why I put this right in the middle of everything, but anyway, we'll use this a bit more later. But let's carry on with what we are talking about here. So now we've got this, so we can see we get this kind of influence. Now let's think about a case where we have a standard kind of Levenspiel plot, which looks a bit like this. And we said before that a plug flow reactor is actually hard to achieve. Plug flow is hard to achieve in reality, right? In plug flow, you are requiring everything to flow as plugs. A much more natural thing for us is to have series of CSTRs, okay? So what happens when we use a series of CSTRs instead of one big CSTR? Is it better or worse? By the way, I haven't been watching the chat. Let me just check there. Okay, so sorry, Siabonga, I missed your message at 2:05. So when we are deriving the equation, do we include the signs for Ri? I think I did talk about this a bit, but did I cover it when I was talking about this? Siabonga. Okay, so yeah, just let me know if we've covered that or you want me to return to that. Okay, so now the question I'm asking here is, let's say instead of using one big CSTR, instead of doing this, let's say we try to use CSTRs in series like we are showing above here, right? Is this better? Is your total volume the same as this? Or is your total volume going to be less, or is it going to be more? Any takers there?
I think for the CSTRs in series will require less volume.
So you're saying the sum of these volumes is going to be less than using one big volume, one big CSTR. Any reasons for that? Can you propose any? Is there a way to see that on Levenspiel? So a way we could look at it is, so let's use little blocks here. So if we do the one big reactor, right, and we want the conversion here, right? So let's say we want to achieve this conversion X star, whatever, right? X star. So we want to achieve this conversion, then with one big CSTR, that's what we'll need. The volume that we need is proportional to this. If we have three little CSTRs instead, let's see what that would look like. So here's the first CSTR, right? So we achieve part of the conversion in this first CSTR, and then we say, okay, over to you, second CSTR. So maybe the second CSTR looks like this. And then the third CSTR, we want to achieve this final conversion X star. So there's our third CSTR. So you see, we are wasting a bit of volume compared with the PFR case, okay, or the batch reactor. We do have this little bit here. We do have this bit of extra volume here. So all this is a bit of extra volume compared with the PFR case. But when compared with the single CSTR case, you see we've now saved all this volume. So definitely having more CSTRs in series, in terms of total volume at least, does save us. So the sum of these three little CSTRs is lower than the total volume required. Okay. You can argue there are other problems with this. For each CSTR, there is significant overhead. You've got that stirrer, and maybe you need control over everything, and there are other costs of having many little CSTRs. That's true, but at the moment we are just talking about total volume. Okay, so that's something that happens. Now, what about using many little CSTRs? And I'm just going to have to draw the whole thing again. So let's draw a Levenspiel plot again. And we have the one big, let's call it a 50 cubic meter reactor. So we've got the one huge reactor. And then let's say we have really tiny little CSTRs, really cute little CSTRs around here. And let's say these are really tiny, like on the order of cubic centimeters, right? And money is no object. We're not worried about all the control that we need to add and all that. We've just got these hundreds of little CSTRs. What's this starting to look like? Even just looking at this picture, does this remind you of anything when you look at it? Right, we'll come back to that. But if you have these,
flow.
Thank you. Yeah, that's what I was looking for. It looks like plug flow. I'll come back to that now. But you've got these many, many little CSTRs here. And you can see now that we are getting very close to the performance we would get for plug flow or batch, right? We are approximately the same as the area under the curve, right? The volume wasted is really little now, has really been reduced. So we are starting to approximate the area under the curve. And you can see the reason for that here. Remember we said for plug flow, we have this tube and we have all the fluid staying in little segregated plugs. So these little plugs, right? And we said each plug was perfectly mixed internally. So in the R direction, each plug was mixed well, but in the Z direction, it wasn't mixed at all. So it was only mixed in the R direction. So each plug was like that. So if you think about 1,000 little CSTRs, each one looks like its own little plug here. So that's looking quite interesting. It looks like we can approximate plug flow-like behavior by changing the number of mixed regions. So that starts to suggest something to us in terms of not necessarily making little networks of reactors, but it starts to suggest a way we can model a real reactor. Because a real reactor is neither one of these two, right? In a real reactor, it takes some time to do mixing. It's not like what we said about CSTRs, everything mixes instantaneously everywhere. In the real world, we have only a finite amount of energy. We can't mix everything instantaneously. So mixing is not so perfect. On the other hand, in the real world also, nothing ever stays stuck in its one with its one group of friends all the time. It learns to diffuse out and mix with left and right. There's dispersion, diffusion, things diffuse around. So in the real world, plugs break apart and they mix as we travel along. And so this is an extreme view, right? Perfect plug flow is an extremum, and perfect mixing is another extremum. But it looks like by putting CSTRs in series, by considering the reaction space not as one big mix zone, but as many little sub-contributing zones, we start to get some kind of in-between behavior. So that's something we can start to think about. Right? So CSTRs in series. We'll come back to this idea as we go. Down here, you can read through the balances that you do in this case. So you can write the balance on a single small CSTR. So that would be like your normal CSTR balance. And then when you want to estimate the volume of the next piece, you acknowledge that coming into the reactor is not the pure CA0, it's CA0 times X1. So that comes into the second reactor, and then leaving that is X2 times the volumetric flow rate. So that so you can calculate the volume of that piece, and then you just add them together. So you can read through this separately about how to estimate your overall, your final concentration. So at the moment, I want to just stay conceptual. So do this separately as well, please. Okay, now now that we know we can do this, that we can get better performance, we can then decide whether, do we want, let's just make a new thing again. So do we want to try to get, so do we want to use multiple reactors of the same volume? So kind of the way I drew it just now. Do we want all these CSTRs to have the same volume, or do we want them to have the same amount of conversion? So maybe we want 0.1, 0.4, 0.6, 0.8. So let's take the easier case first. Let's say we simply choose to have the same conversion each time, right? Then we can say the conversion we achieve in each CSTR is simply the overall desired conversion divided by the total number of CSTRs. So if we've chosen we want 3 CSTRs and we want a conversion of 0.9, then 0.9 divided by 3, we need 0.3 of a conversion in each CSTR, right? So if we've chosen that, then it's a simple matter of just evaluating the volume in each case, right? So that's kind of straightforward. That's what we've been talking about. But it might be the case that, well, we are not free to choose any volume, right? So it might be the case that we can't say, oh, I want to choose that conversion, right? It might be the case that we are told, well, what I have on my shelf here. So let's say you are in a reactor shop and you were told, okay, today I only have 2 cubic meter reactors for you, right? So you are stuck to 2 cubic meters everywhere. So then how do we navigate our way on this Levenspiel plane? So let's go back to the equation and see here. So we can see simply that for the ith reactor in the train, the volume of that ith reactor is the difference between the exit and the inlet, right? The conversion difference there, and then the reaction rate in the reactor in that ith train. Please note carefully, this reaction rate does change as you consider, as you look at different reactors in the train, obviously. So what we have to do there is, if we are given the conversion, if we are given the volume, if we are told, no, you can only have this volume reactor, then what we have to do is, obviously we start with a conversion of 0 here. And then, so you have a 0 for the first reactor. And then we can look up at the 0 point for the reaction rate. So we can look here, we can see 1 over RA is this value. So that's defined. So that's a number that we have. This is fixed, right? Your inlet molar flow rate, we have been assuming we know that. So the only variable left over is this one. So we've been told what the volume is. The starting conversion is 0 and we read off RA. So the only thing to work out is that. So we can then work out what that first conversion is, right? So that defines the first conversion, and it won't necessarily be the one we want. And then we say, okay, let's buy another one, another 2 cubic meters. And then this time we use the previous conversion, X1, and we then look up the reaction rate at that point X1. So now we've got a slightly different reaction rate over here. So that's RA in reactor 2. And then, so everything is defined. We stuck to our 2 cubic meter in our reactor shop. We've got this and this, and then we can work out XA2. So that defines the next point. And we just keep going like that. And so what will happen is you'll get progressively thinner slices as you go. So because it's a CSTR and it still has its issues, it will take a greater and greater volume to get the same conversion increases. or using the same volume increases. Okay, so your slope defined like that will change each time. Okay, any questions or comments there? Okay, so that's the case if you don't have the ability to choose the volume. I just want to check, how are we on time? When are we supposed to do? Okay, I think I'll just keep going until you complain, right? Okay. So here we are trying to be a bit cleverer, right? So here we are saying, well, I've got my workshop, they can make any volume that I want, but still I want to take advantage of these CSTRs in series. I know I get better performance using these CSTRs in series, but I don't want to just wing it, right? I don't want to just hope for the best that I'm just going to either use equal, that I'm just going to use equal conversions or equal volumes. I know that there must be an optimal choice. What is the best X value to choose such that I get overall the smallest possible combination of reactors, right? So now we're trying to be really clever with this and choose a really good intermediate conversion here. So the way that we do that is say, well, the wasted volume is this volume, right? We know when we use two CSTR, for example, two CSTRs in series, that's the wasted volume. So we can switch this around and say, well, then let's try and minimize the wasted volume. So I'm at the moment, I'm restricting myself to only two reactors. So given I have two reactors, but I can make any volume I want, then how do I best choose these two reactors? So what's my optimal conversion, the optimal intermediate conversion? So to minimize this, we're going to take a quick detour here. And we're going to say, okay, if I have a curve like this, so just generally in y and x, if I have this function y of x, then how do I maximize this volume? How do I maximize the area if I pick some point x? So I've got some curve y of x, and I can pick any x value. So I want to pick a value for x, which is going to maximize this area, right? So what's the value of x that when you choose it and you draw a box using that point and the origin, what's the value of x that maximizes that box? And you can think, you know, if you choose x right down here, then you've got that box. That box is clearly smaller than this box. On the other hand, if you choose an x value right over here, then you've got a thin slice like that. So that box has a smaller area also. So between those two, but in this range here, in between somewhere, there does exist an x that will maximize this area, right? And the way to figure this out is to say, well, clearly the area is y times x. And so the rate of change of that area is maybe let's do it separately here. So the area, so given function y equals y of x, the area of the block at or with corner points 0, 0, and x comma y of x is, so the area of that is clearly just x times y. So the derivative then, or the differential area, is equal to di A. So we can do this as partial A partial x dx plus di A di y dy. Right, you agree the overall, as we consider different x and y values, the change in area looks like that. And so di A di x, you can see, is simply y. So this is equal to y times dx plus, and then di A di y, you can see here, di A di y is x, and that's times dy. And we are looking for the place where di A or di A di space is equal to 0. So the maximum area is going to be where this equals 0, or this is where di A or di y or dy dx equals y over x minus y over x. Right, so if you look at this part, you can see if you take, for example, x dy on the other side, and then you take dy dx, then you're going to have to divide by x on both sides, and you'll get y over x. So you'll get that form. Right, and if you look at this, this is nothing but the tangent, which looks like that, right? So your slope at yx, that is this tangent, or am I saying this properly? So the position where you get the best, the biggest area is where your slope is equal to this, right? So dy dx is the slope, right? You've got some curve here, and you've got a slope, and of course the slope is minus dy dx, right? So you've got that slope, and then where it's equal to y over x. So you can look up different points here. You can pick a point here, for example, you'll get a certain slope. You'll check that slope. Is the y divided by x value there equal to the slope? And then you say no, then you check the next point. Let's draw that separately. So here's here's a drawing like the one that we saw there. So you've got this curve. Maybe let's draw it a bit more like this. So if we pick a point, let's say here, then you get the slope here, and then that slope, right? So that derivative, whatever it is here, the slope is approximately 0, you can see. And then you look up the y value divided by the x value there, and you'll see, okay, this y, if I take this value of y divided by this value of x, and I compare it with that slope of 0, I'm not getting, they are not equal. So y over x is not equal to the slope here. And then if I take a point here, for example, and I look at the value of y here divided by the value of x there, and I compare that with the slope, then you see, okay, that's not equal either. So, but there will be a point somewhere in between where this gradient is equal to this ratio of y divided by x. And at that point, you will get the maximum area. So that's where you can maximize the area. And then in terms of what we are trying to do, we are also trying to maximize this area. So we can use the same approach to figure out the x value where we maximize this area, or we maximize the volume that's saved. And so we do exactly that. We try different x values. So you can simply pick different x values here, and you look at the slope that you get. So what's the slope at this point? And then what's the area at that point? So that's how you can maximize that. You could also just try taking a couple here and just try and get calculate the area each time, and you can just brute force go and look for the biggest area there. Well, anyway, I guess that covers it. So I didn't want this kind of clever thing to take up all the time, but that's how you can really optimize your design. You can really get the smaller size reactor like that. Okay, does that cover it? I'm asking as if you asked a question. Any questions or comments there? Okay, so that's that one. We've talked about this, infinite CSTRs in series. Here it shows a bit more rigorously what we said generally. So if you have n identical CSTRs, you'll write it like this, and then you can say, let's take the limit for n going to infinity. Then it looks like this. And then if you look at this equation, you basically have this form, and you recognize this as the exponential function. So as much as we define the exponential function through the natural log, which itself came from integrating 1 over x, we can also find it through a kind of a Taylor type approach. And so you can show this expression. So just check your first year maths notes. You'll see that at some point you derive that the exponential value can be approximated in this way. So if you look at this expression that you got directly from the CSTR design equation, right? If you go back and check your CSTR, you'll see that's what you get here. When you look at the limit for n going to infinity, you get something that looks like an exponential here. And if you check the PFR or the batch reactor design for the first order reaction, you'll see you get the same equation. So at least for the first order reaction, we can also show rigorously mathematically that you get the right equation as you let the number of CSTRs go to infinity. So you can rigorously prove this also. So do work through this carefully and see you can prove that. Okay. So I want to stop there today. This does cover the Levenspiel plot. And then in the tutorial, there was a question on Levenspiel in tutorial 2. There are more questions like this in the new tutorial that I put out. Okay, which I haven't put out yet, but I'll put more tutorial 3 questions, which will have more about Levenspiel type questions. And so those are what you can submit by next week. Okay, any questions or comments there? Okay, then I guess that's it. So I'll see you next on, what is it, next week, Tuesday. All right, so that's it for today. Thanks, everyone. See you next time.